So hello everyone. Today I am going to talk about the role of shear and bending analysis in UAV lightweight design. So unmanned aerial vehicles or UAV are increasingly important in modern aviation. They are used for surveillance, defense, agriculture, delivery, and even disaster management. But one thing is common across all these applications. UAVs must be lightweight to fly efficiently, yet strong to withstand all the forces acting on them. Now, designing something that is both light and strong is not easy. If we focus only on strength, we might end up using heavy materials, which reduce efficiency and flight time. If we focus only on lightness, the UAV might fail structurally. This is where structure analysis comes in, especially sharing and vending analysis, which helps in find the right balance. In this presentation, I will walk you through why shear and vending are so important, how they affect UAV structure, and how engineers use them to create lightweight yet safe design. So, talking about the importance of structure analysis, let us first understand why structure analysis is important. Every UAV has wings, a fuselage, and a tail. These parts are constantly exposed to aerodynamic forces such as lift, drag, and aerodynamic pressure. So, talking about the shear force, it acts like internal sliding force inside a material. Imagine trying to slide the top of a deck of card sideways. The cards slide over one another. That's the shear. And bending, which happens when a structure is forced to curve under a load. Imagine holding a scale at one end and pressing down at the other. It bends. If engineers ignore these forces, two things can happen. The UAV may fail during flight, which is dangerous and costly. And the second one, designers may add extra material just to be safe, making the UAV unnecessarily heavy. That's why understanding shear and bending is critical. It helps in designing a UAV that is both safe and lightweight. So now, talking about the shear forces in UAV. Shear forces mainly occurs in wing spars and fuselage joints. The wing spars is like the backbone of the wing. It carries load from lift and transfers them to the fuselage. Under flight conditions, it experiences shear forces if not properly designed. The spar can suffer shear working, leading to wing failure. The fuselage joints connect different sections of the UAV. These joints often experience uh, shear due to uneven loads. Poorly designed joints can fail, leading to catastrophic results. For example, in some early UAV prototypes, engineers underestimated shear force in fuselage joints, leading to crack during long endurance flight. That showed the importance of detailed shear analysis. So, analyzing shear ensures the material can resist these internal sliding forces without buckling or cracking. So now talking about the bending in UAV structures. Now let's talk about bending. UAV wings bends mainly due to lift forces. As the wing generates lift, the upward force bends the wing upward. If the bending is too much, it can affect aerodynamics performance. And the tail and fuselage also bends, but here it is mostly due to aerodynamic pressure and turbulence. Why is bending analysis important? First, it prevents excessive deflection. If the wing bends too much, it changes the angle of attack, which can make the UAV unstable. And the second one, it ensures flight stability. A wing with properly designed bending system may flutter or even lose control. A real world example like a commercial aircraft wing are designed to flex upward several meters during flight. This is safe bending, but uncontrolled bending, especially in smaller UAVs, can lead to instability. That's why engineers carefully calculate allowable deflection. So now, talking about shear and bending interaction. Now here is something important. In real life, shear and bending never act separately. They occur together. Uh, Taking the example of wing spar again, it carries shear from lift. At the same time, it experiences bending from drag and the weight of the UAV. If we only analyze shear or analyze bending, we miss the complete picture. That's why engineers always do a combined analysis. It's just like testing a bridge. A bridge does not only face car moving across like shear, it also has to handle bending due to its own weight and wind loads. Only a combined analysis ensures safety. For UAVs, this combined shear bending analysis is essential for realistic design. So now, talking about the role in lightweight design. So how does all this help in lightweight design? Material selection analysis helps us decide whether to use carbon fiber, aluminium, or composites. Carbon fiber is lighter and stronger, but more expensive. Without analysis, we might either choose the wrong material or add unnecessary reinforcement. And weight reduction. Properly analysis tells us exactly how much material is needed. The way we reduce weight without losing strength. Optimal design, it avoids two extremes. Over design. Adding too much materials makes the UAV heavy, reducing endurance and payload. And under design, using too little material risks structural failure. So shear and bending analysis is like finding the sweet spot. Just enough material for strength, but not more than needed. And now talking about tools and methods. To perform these analysis, engineers use different tools and methods. Where the first one is finite elemental analysis or FEA, a computer-based method that divides the UAV structure into tiny elements and calculates stress and deformation. It is highly accurate. And the second one is beam theory, a simpler traditional method where the wing or spar is modeled as a beam to quickly estimate shear and bending stresses. And the third one is CAD and CA integration. Computer designs and engineering tools allow direct simulation of UV parts. For example, engineers can simulate wing bending before building a prototype. And the fourth one is experimental testing. No matter how good the computer analysis is, engineers always test in real world. This includes wind tunnels and static load testing, where wings and fuselages are subjected to real loads to check performance. By combining theory, software, and testing, UAV designs are validated for both safety and efficiency. So now, considering a case example of a UAV wing spar. Without analysis, engineers might play it safe and use a thick aluminum spar. Yes, it is strong, but it is also heavy. The extra weight reduces the UAV flight time, but with shear and bending analysis, engineers can optimize the design and use carbon fiber, reducing weight by about 30% while keeping strength intact. And this optimizes translate directly into better performance. The UAV can carry more payload, fly longer, and consume less energy. This is clear example of how analysis directly affects UAV performance and mission success. So now, talking about the challenges. Of course, performing shear and bending analysis is not without challenges. Accurate modeling of complex loads. In real life, loads are not simple. They vary with speed, altitude, turbulence, and maneuvers. Simulating these loads accurately is difficult. And the second one is balancing cost versus performance. So advanced materials like carbon fiber are excellent, but these are expensive. Engineers have to decide whether the performance benefits justify the cost. And the third one is ensuring fatigue resistance. UAVs may undergo hundreds of flights, but even if a structure handles shear and bending once, repeated cycles can cause fatigue. Designing against fatigue is challenging but necessary. These challenges remind us that UAV design is not just about theory but also about practical compromises. So now, in the conclusion, to conclude shear and bending analysis, forms of backbone of UAV lightweight design. It allows engineers to maintain strength and durability, reduce unnecessary weights, and improve flight time and payload capacity. Without this analysis, UAVs would either be too heavy to be efficient or too weak to be safe. So the role of shear and bending analysis is clear. It ensures UAVs are light, strong, efficient, and reliable. So thank you for listening. Have a good day.